So we have part 284C3M1B7C8E13C9C6D3P38D19D7b49. And this is the line of data is line 22f1fa19c3m1b7c8e13c9c6d38d19d7b49. SAMMY, which is in capital letters, SAMMY, so it stands for something. Pulse sequence signals 5G Wow Seti. There's the alien radio signal, and here's the data. Okay, so this is about the SAMP4, I don't know if it's 14 or SAMP4 pulse sequences. SAMMY was SAMMY. SAMMY communications device keyword research. In UFO spaceship WOW data. I'll type that. It's done on May the 13th, 2013. Today is the 26th. So the previous video was this line of data, broad spectra optical fiber high power. However, we're working on the quote PDF file results from a blog. The keywords were mid-infrared optical frequency combs at 2.5 ohm based on crystalline microresonators. Then we looked at chalcogenide fibers, and that came up in this line of data, Telecom wavelength semiconductor signals. And then I've got to repeat it, all of them. That's crazy. Okay, I don't know how I did that. So the original video is number 37. So if you take this line of data and just change the last two numbers to 37, you'll get to the very first one where it's talking about these type of signals. So it's mid-infrared optical frequency combs. Then we went to the mid-infrared oppo pump laser. Then we did a high power comb line. Then a phase noise infrared signals. Then I did infrared comb nodes frequency signals. Then frequency comb spectrum signals. Then telecom wavelength semiconductor signals. Then we did the Telecom's viburnum doped fiber signals. Then chalcogenide polycrystalline fibers. And then chalcogenide glass frequency signals formula. Then we did high power silica cables diode lasers. And then broad spectra optical fiber high power. Quote PDF file from the blog was selective averaging for high resolution solid state NMR spectroscopy of aligned samples. From those two scientists, and it's from Gilman, La Jolla, California. And there's the link there. So abstract. Solid state NMR experiments benefit from being performed at high fields. And this is essential in order to obtain spectra with the resolution and sensitivity required for applications to protein structure determination in aligned samples. Since the amount of RF power that can be applied is limited, especially for aqueous protein samples, the most important pulse sequences suffer from bandwidth limitations resulting from the same spread and chemical shift frequencies that aids resolution. SAMP14 or SAMP4. Oh, SAMP. I think it looks like an I or an L. I don't know. SAMP and then I or L4 is a small sequence that addresses these limitations. It yields separated local field spectra with narrow and more uniform line widths over the entire spectrum than the currently used PISMA. That's P-I-S-E-M-A in capital letters, so that stands for something, and SAMMY, S-A-M-M-Y, capital letters experiments. In addition, it's much easier to set up on commercial spectrometers and can be incorporated as a building block into other multi-dimensional pulse sequences. Now, remember that at the very beginning we talked about a new universal standard model, a new building block of matter. Now, the keyword building block comes up here with multi-dimensional pulse sequences. We were talking about second dimension, third dimension, fourth dimension, fifth dimension. And now we're talking about pulse sequences from these different dimensions. So that's kind of cool. So this is illustrated with a two-dimensional HET core, H-E-T-C-O-R in capital letters, which again stands for something, experiment, where it is crucial to transfer polarization from the amide protons to the directly bonded nitrogens, over a wide range of chemical shift frequencies. A quantum mechanical treatment of the spin Hamiltonians under high power RF pulses is presented, which gives the scaling factor for SAMMY 14 as well as the durations of the RF pulses to achieve optimal decoupling. So the keywords are selective averaging, average Hamiltonian theory, separated local field spectroscopy, homonuclear decouplings, SAMP14, SAMMY, and plasma. So figures and tables from this article, we got CP, odd T1 dwells, and even T1 dwells. And then it's got these X's and Y's and numbers. I have no idea what that means. So this is talking, figure 1 is a timing diagram for the SAMP4 pulse sequence. Also it's showing the pulse sequences. Only one phase alteration on the low side is used. So I guess I'm assuming that's the low side, which decreases the number of phase transients. The length of each interval corresponds to the durations of the RF pulses as shown. So obviously the way we do the laser pulses and then we diffract them is going to create some sort of electronic messaging device. So this is a communications device. So I'm assuming the pulse, if you do it in different intervals, it could probably eventually we figure out how it can spell out letters. Right? Kind of like you did with your telegraphs, your early telegraphs back in the war. I forget what the name of that stuff was called. SOS. Oh yeah, maybe it is called a telegraph. That little machine that you tap, 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 and you do a long line, short line, long line, short line. It means things. So now you're going to integrate that kind of technology in with these pulses. Oh, that'd be cool, eh? Because everybody knows that earlier technology, because that's an emergency technology that we revert to when, well, according to your science fiction movies, whenever there's a big disaster and we can't use our normal electronics, we go back to the old school tap, tap, tap stuff. So the phases of event T1 dwells are 180 degrees phase shifted compared to that of the odd dwell. To compensate for the finite Y90 pulses in the middle of each dwell, and then there's those funny little symbols with numbers, and there is a formula there with pi in it, and pi comes up before, and Y and X axis has come up before as well. So this is showing different timing diagram for the SAMMY pulse sequence 22 in the squiggly line pulse approximation. So that's what it shows. The length of each interval corresponds to the durations of the RF pulses as shown. Okay. So their next figure is A and a B, and it's got numbers 0, plus, and then minus numbers to 10 on both. And oh, it says 1H 15N Doppler coupling KHC. Okay. So this is figure 3, simulated spectra corresponding to the heteronuclear dipolar coupling frequency dimension of separated local field spectra. Those are different signals. So that's 2 going up, 1 going down. Okay. A. So this is the A. On this side, 2-body simulation of idealized SAMMY. B is this one here. This one with the down signal. 12-spin many-body simulation of SAMP4, SAMP4, or SAMP14. I don't know if it's a 14. I can't tell if that's a 14. It's bugging me. I don't know what it is. In both cases, A and then the little word max was set to 10 kilohertz, and a 5 ms exponential decay function was applied to the calculated FID in the dipolar dimension. So you were using alpha decay techniques with the Higgs boson signal. So if we integrate the Higgs boson signal with this SAMMY type pulse technology, I wonder what you would get. The magnitudes of the observed doublets are approximately 9% larger. Actually, I'm going to write that down before I forget. So you want to take the pulses of SAMMY and add it to the Higgs boson signal. Create lines of data with long or short signals like a telegraph. I'll put that in the notes when I video came during filming. Filming May 26, 2013. There. Okay, yeah, I'm just mumbling here to myself because I'm making notes. Which I've got to bold and make 16. Okay, so I'm just going to cut this and put it in here somewhere. Probably add this to my thoughts. Sorry, I had some thoughts, so I'm going to just, if I don't do this, I will forget. Okay, so the magnitudes of the observed doublets are approximately 9% larger, which agrees with the scaling factor of EQ12. Note that the small doublet present in the middle of the spectrum disappears in the many-body case. Should move that up there, right? I have this certain little way of doing everything, and it's got to be done that way or else. And then you don't like it. I know, I'm a pain in the butt, but that's the way I am. It's got to be done a certain way. Okay, so here's another figure here, which I can hardly barely see. It's so puny. Let's make it bigger. Okay, so this has got... okay, so this is a figure 4 timing diagram for the core, HETCOR, capital letters, experiment incorporating SAMP14 or SAMP-L4 to achieve selective polarization transfer. Okay, so we've got a timing, we've got an experiment, and we've got a polarization transfer. So I'm going to add that up here. I'm going to add polarization transfer. Because what we want to do is we want to transfer signals. Oops, let's go back up here. What we want to do is transfer signals, right? We're going to transfer signals from the micro wires and combs nodes to communicate with one another, generating electricity for the UFO spaceship, and creating words or messages when beamed outside of the spaceship. How's that? To Earth. From wherever. From La La Land? No. From outer space there. Yeah, I'm thinking as we go along. Okay. I've decided to do it this way because I've got so many projects on the go. I don't have time to go through this data and find it. I usually skim over it, look for keywords, and then I just use the information. And then I kind of evolve stuff as I go along, right? So I'm going to show you how I do this. So during the T1 period, let's see, where's T1? T1 is this little circle area here. This is T1, and this is the NSAM, and this is T2. So these are the different results. There's the calculations there. I'm sure you guys know what this is. I have no idea what it is. Looks interesting, though. Okay, so during T1 period and the 1H chemical shifts. I have no idea where 1H is. Your guess is as good as mine. Evolve under conditions of FSLG, decoupling, and high power continuous RF irradiation of at 15, n to the power of 15 on the left side of the n. I don't know. Okay. So the third intermittent Y90 pulse, you guys must get a kick out of the way I read this. Seriously. The third intermittent Y90 pulse after T1 evolution pulse interleaves real and imaginary parts. The optimal number of SAMP 14 cycles is between 4 and 10 in this application. So here's figure 5. We're going to compare comparison of SAMP 14 and SAMMY. Oh, it's two different things. Okay, that you probably knew that, right? Of a multi-crystal sample. This is good. We always talk about crystals in lattice and mesh in this communication design. Consisting of 3 single crystals of NaL at arbitrary orientations. So let's look at the data here. We've got there's our 15N shift, ppm, and that's 1H to 15N dipolar CPIG kilohertz. That's the beat. Looks like sunspots. It does. I do sunspots all the time on my predictions thing. I'm running out of battery power, and I'm only halfway. Okay. SAMP14 spectrum, the contour lines correspond to the two-dimensional power pattern calculated using the average 15N CSA tensor parameters. So that's all Lorentzian line widths. Then there's another figure, comparison of plasma with 2 for 1 each carrier frequencies. Talks about optimal decom. Let's go back down to the lines here before. Oh, there's lots of data here. I'm not going to get through this before my battery dies. So it's from www.sciencedirect.com, and SAMP14 and pulse sequence. There's several videos on it. So it's got 2-dimension solid state NMR spectra, 90-degree pulse calibrated at 5.3 US. The contour lines show the power patterns expected for immediate resonance and perpendicular bicells, including bicell order parameter of 0.8. Signals that fall outside the contour lines are side chain resonances. Okay.